Very good afternoon to all of you. I'm Piyush Kumar. I'm from IT Delhi, and contents for this work. First, I will introduce the concept, then working principle, designing of the device, then fabrication. After that, we will discuss experimental results, comparison with the other literatures, and finally conclusion. So going to the next. So as Dr. Sheena and Ms. Priyanka already presented about and give a short introduction about NEMS-based NEMS and MEMS-based sensor. So right now I'm just moving towards the what are the challenges we are facing in MEMS and NEMS devices. So first of all, in every MEMS and NEMS devices, we face stiction failure related to the surfaces of the both of the and one static part and dynamic part. So what are the cause of stictions? They happens due to when adhesion forces surpasses the restoring force of suspended structure. It happens the stiction failure. And what are the impacts of stiction? That decreases its performance. Also, it causes the complete failure of the devices. So we need some improvement. Already some people did some improvement related to like they introduced some bumps, some extra coating. But here we are proposing an piezoelectric reset mechanism that can work using a piezoelectric material to actuate or deactuate it. So here in picture, pointer to be there. Pointer.
Basically, you have to long press it and
okay. So during excessive vibration or shocks, okay. So when we see a suspended beam or a cantilever beam like this, so here if it sticks on, suppose it sticks on the sensing electrode or whatever we call sensing electrode. So here we proposed a thin adhesion layer, and beneath that a piezoelectric layer that that can reduce the failure mechanism of every piezoelectric MEMS sensor. So here in adhesion locking, during excessive vibration or shocks, the beam adhere to the dome-shaped reset electrode, restricting movement due to higher adhesion force compared to restoring forces. So how reset operation works? A reset pulse of 15 volt is applied to the base while the beam remains grounded. The piezoelectric material beneath the beam vibrates and reducing the contact area between the cap and dome-shaped reset electrode. This also reduces adhesion forces, allowing the restoring force to dominate, returning to its original position. So we designed this device on the basis of adhesion force of first of all for using adhesion force and using the restoring force of that device. So total contact area is equal to area of base one and area of piezo one. So finally adhesion force will be like this one. And the fabrication steps are as follows. First, we deposited 50 micron thin film of moly, then aluminum nitride using sputtering. Further, to reduce the stiction, we also deposited L2O3. Then finally, the sacrificial layer that was aged using buffer hydrofluoric acid. Finally, finally the fourth level of lithography happens, and top beam was suspended using vapor HF. So finally we get such kind of structure where we can see, my pointer is here. Here is the aluminum nitride ball shape kind of structure that can deactuate the top MEMS beam, and it can suppose this beam sticks to the sensing electrode. So previously it was like a failure case. Now using this concept, what we can do, we can just supply 15 volts, and it will again it will restore to its original state. Then again, now every MEMS device will be started to work fine. Here we can see this such kind of ball shape of structure we can get using this reset mechanism device. Here are the results. If we see the current versus voltage curve, so from this reason, if we increase the voltage, current is like almost 0 microamperes. So if we on this point, pull-in will occur, and if pull-in occurs and adhesion force is like much dominate to restoring force, it will just stuck here, and my current will be going further. So this device will, in this case, the red arrow shows, in this case, device failure will be occur. And by supplying the reset voltage that we proposed, it will come back to the original position, like this one in the second graph. Previously, it was like 1 ampere. Its current was 1 ampere. Now, just supplying 15 volt, again it goes back to its original state, and the suspended structure still stand alone to its initial state. So current value remains back to 0 volts. In the next slide, here is a comparison table where several parameters are there, and different methods were used previously to employ such things to reduce the failure. So here in our proposed mechanism, we used a piezoelectric pulse over some stiction, and here area utilization was like we needed just a small area. Yes, it is a CMOS compatible. Durability was also high, and cost is medium. We have already successfully tested the devices more than 1,000 times, and it was a successful device. Finally, conclusion: innovative reset mechanism has been introduced using a novel piezoelectric reset mechanism. Successfully designed, overcome stiction in MEMS-based pressure sensor fabrication and characterization has been done. Validating and testing cyclic current voltage sweep using effectiveness of the reset mechanism in storing the beam after stiction events. More than 1,000 successful cycles has been already done. And the robust and efficient, that is the robust and efficient solution for most of the MEMS sensors. So this such kind of device provides a great energy efficient approach also to realize MEMS-based sensors to just to its robustness. Okay, thank you.